Okay, so we're going to talk about improper integrals. What makes an integral improper is when we contradict what we originally set forth as the guidelines for an integral. Okay, so when we originally defined our integrals, we dealt with a continuous function on a finite interval. So we're going to talk about what if our function isn't continuous and what if it's not on a finite interval. Okay, so we're going to start by talking about an infinite interval. So I want to consider the infinite region that lies under the curve y equals 1 over x squared above the x-axis and to the right of the line x equals 1. Let's take a look at what this looks like. Okay, so I have the graph of y equals 1 over x squared, and I want the region above the x-axis and to the right of x equals 1. Okay, so I shaded the region that we're talking about, and first of all, we should just talk about, is it possible for an infinite region to have a finite area to it? And our intuition should probably tell us no, an infinite region can't have a finite area. But if you look at this little region that I graphed in here, it does go on infinitely, but look how tiny it's getting towards the end of the graph as x gets big, and I haven't gotten anywhere close to the end of the graph. I just went over to x equals 9. So we want to talk about whether or not this infinite area can have a finite region, and if the answer was just no, then our lesson would be over. So let's investigate a little bit more. I want you to go ahead and write me an integral that would describe the region that I shaded, the region above the x-axis, under y equals 1 over x squared to the right of the line x equals 1. Pause and come back to me with your integral. And you should have come up with the integral from 1 to infinity of 1 over x squared dx. Okay, if you think about what we have to do with this integral, if I take the antiderivative and then plug in upper minus lower, I'm going to be plugging infinity into a function, and I can't plug in infinity. What can I do with infinity? What have we done when we want our numbers to, well, they can't be equal to infinity because it's not a value, but they can approach infinity, okay? And even that word of approach should tell you that I need to do some kind of limit, okay? So what makes this integral improper is the fact that I have an infinity for a bound, and I need to get that infinity out of the bound. So my first step is going to be to make a little substitution and to let that bound approach infinity. And that would look like this. Okay, so I have the limit as t approaches infinity of the integral from 1 to t of 1 over x squared dx. Once you get to this place, you can go ahead and integrate. You're going to hold that limit out front until you actually evaluate the limit. So again, keep pausing and try. So just take the antiderivative, okay, and just recognize that this 1 over x squared is my x to the negative second. So I can go ahead and integrate. I'm going to hold the limit. I'm going to hold the bounds. I'm going to integrate that and pause and come back. Okay, so when I integrate x to the negative second, I should come up with an x to the negative 1 over negative 1. Okay, which is negative 1 over x. So when I evaluate that, it should look like this. I have the limit as t approaches infinity of negative 1 over x from 1 to t, and I'm going to do upper bound minus lower bound, pause, and come back. Okay, you kept the limit, and so you have the limit as t approaches infinity of upper minus lower. I get negative 1 over t minus negative 1 over 1, or the limit as t approaches infinity of negative 1 over t plus 1, okay? And now once I got a simple algebraic expression here, I can take the limit, and if t is approaching infinity, 1 over t is going to be approaching 0, and I'm left with a value of 1, okay? And so that means that this infinite area does have a finite value, and that finite area is approaching 1. Okay, so let's just talk formally what the rules for improper integrals are when I'm working on a finite interval, I apologize. So if the integral from a to t of f of x dx exists for every t greater than or equal to a, then we say that the integral from a to infinity of f of x dx is equal to the limit as t approaches infinity of the integral from a to t of f of x dx. I know that sounds like a lot of mumbo jumbo, but pretty much what that means is that when I have this as my setup, then I take this integral, okay, and if I get a real finite number for that limit, we call the integral convergent. Otherwise, it's going to be divergent. And we also have a case that if I have infinity for a lower bound, I would just replace the lower bound with a t and take the limit as t approaches negative infinity. Okay, so let's look at some more examples. Okay, let's look at the integral from 1 to infinity of 1 over x dx and decide if it's convergent or divergent. Okay, so let's start by setting up with our limit. So go ahead and pause and get rid of that infinity for a bound and rewrite that properly. Okay, so I should have the limit as t approaches infinity of the integral from 1 to t of 1 over x dx. Okay, just pause me every step, evaluate the integral, and come back. Okay, the integral of 1 over x dx is natural log absolute value of x. Okay, I keep my limit, so I have the limit as t approaches infinity of natural log absolute value of x from 1 to t. I'm going to plug in upper minus lower, pause, and come back. Okay, so you have the limit as t approaches infinity of natural log of t minus the natural log of 1, and since natural log of 1 is 0, I end up with, we just have the limit as t approaches infinity of natural log of t, okay, and either think about graphically or think about what natural log function means, but as t gets bigger and bigger, so will your natural log function, so that means that the answer to this is, pause, think about it, and come back, infinity, okay. We are not getting a real finite number, so this integral is divergent, okay. So when we get a real finite number, we have convergence. When we get a infinity, we have divergence. Let's do another one. Let's take the integral from negative infinity to 0 of x e to the x dx. Okay, so our first step, again, because we have infinity for a bound, is to rewrite so that we do not have an infinity for a bound. So go ahead and do that. Try to work through the problem. I'm just going to throw up the solution pretty quickly. Just be careful when you're integrating this. We just learned recently how to do this integral. Okay, a normal u sub is not going to work for you. So I have the limit as t approaches negative infinity, the integral from t to 0 of x e to the x dx. I hope that you realize this was an integration by parts problem. I'm going to quickly do it by tables. So my tables would have looked like this, okay, and then when I go and put that together, my integral would be x e to the x minus e to the x, and I'm going to throw that with my limit and my bounds, and I would get this. The limit as t approaches negative infinity of x e to the x minus e to the x from t to 0, and if I do upper minus lower, I get, and that gives me this, okay, which can simplify to, okay, so that first two terms, the 0 minus e to the 0, is going to simplify to be a negative 1 because e to the 0 is 1. I want to consider the limits for these two pieces separately, okay, because it can be a little bit confusing. So just as an aside, I want to consider the limit as t approaches negative infinity of t e to the t. Okay, and this is a limit that we actually discussed specifically when we were talking about our, when we talked about L'Hopital's and our limits at infinity. If I think about plugging into this, I'm taking very large negative values and multiplying it by e to a very large negative exponent. It'd be much simpler if I saw this limit as the limit as t approaches infinity of negative t over e to the t. Okay, and the reasons these limits are the same is because I still have a negative infinity over, well, times e to a negative large exponent, which is the same as 1 over e to a large exponent. And now that I have this limit, I can either do dominance or L'Hopital's, and either way, I will get an answer of 0. Okay, and if that limit is 0, that means that, okay, so that component is approaching 0 over here. And then my other limit as t approaches negative infinity of e to the t, I want to consider that separately too. Okay, and if I have e to a very large negative exponent, it's the same as 1 over e to a large positive exponent, and that's going to approach 0. Okay, which means if I go back to my original limit, I end up with negative 1 minus 0 plus 0, which is negative 1. Okay, so this integral is going to converge to negative 1. Okay, so here's a weird situation for another example. I have the integral from negative infinity to infinity of 1 over 1 plus x squared dx. Okay, here I have I have a doubly improper integral. Okay, I've got two infinite bounds. So I need to break it up so that I can look at one improper integral at a time. So I first need to rewrite this as the integral from negative infinity to 0 of 1 over 1 plus x squared dx plus the integral from 0 to infinity of 1 over 1 plus x squared dx, because I need to deal with each infinite bound at a time. I picked 0 to split it up because it's a nice number that's between negative infinity and infinity. But it really doesn't matter where you split it, but it's going to be easier to evaluate using that 0 value than any other value. Okay, when you have to split into two integrals, just work one at a time, because if you come up with either integral to be divergent, then the entire problem is divergent and you don't need to look at the other side of it. The only time that you should do the second integral is if you come up with a convergent value for the first, and then you'll probably come up with a convergent value for the second. Okay. So I'm going to just work one of these integrals. I'm going to start with the positive integral from 0 to infinity of 1 over 1 plus x squared dx, just because it's going to be a little simpler. So please look at that integral and rewrite it so that you don't have an infinity as a bound. Pause and come back, and you should have something that looks like this. Okay, the limit is t approaches infinity, the integral from 0 to t of 1 over 1 plus x squared dx. Okay, when you go ahead and try to integrate this, it is a composite quotient. If you try a traditional u sub, it doesn't work, so rack your brain to think about what the antiderivative of that function is. Pause and come back, and hopefully you will have realized that my antiderivative is inverse tangent. Okay, so now I'm going to do upper minus lower. You'll have the limit is t approaches infinity inverse tangent t minus inverse tangent 1. Let's just talk about what inverse tangent 1 is. Okay, I want sine over cosine to equal 1. I want opposite over adjacent to equal 1. Inverse tangent of 1 is going to be happening at pi over 4. Okay, let's talk about what inverse tangent of infinity would be. Okay, so inverse tangent of infinity means when are my tangent values getting really, really, really large? And if you think about the graph of tangent, we have all those vertical asymptotes throughout the graph. But if you remember that the range of inverse tangent is only from negative pi over 2 to pi over 2, the first time that I go up towards positive infinity is at pi over 2. Okay, which means that this is really pi over 2 minus pi over 4, which is pi over 4. Okay, again, I want you to think about what inverse tangent means and why I'm coming up with those values, and it should make sense to you, hopefully. All right, so now that I'm coming up with a convergent value for actually it's my second integral, I need to go back to that first integral from negative infinity to 0 and try to evaluate that. I'm just going to, so pause, and I'm going to have a completed answer for you when you come back. Okay, so I'm going to have 0 minus, I have my integral, I take my limit, I take my antiderivative, I get inverse tangent again. I'm doing upper bound minus lower bound, which made me realize I made a mistake in the first one. I'm going to fix that in 1 second. I have inverse tangent of 0 minus inverse tangent of t. Inverse tangent of 0 is 0 because tangent of 0 is 0. And then inverse tangent of negative infinity is asking you where is your tangent graph approaching a vertical asymptote but going down towards negative infinity. And that's happening at negative pi over 2 because, again, the range of the tangent function is from negative pi over 2 to pi over 2. So I have a 0 minus negative pi over 2, which is pi over 2. Now let me go back and fix that first integral because for some reason I changed my lower bound to a 1 in place of a 0. So let me go fix that. Okay, so I changed my lower bound to a 0, and inverse tangent of 0 is asking where sine over cosine is 0, and that's happening at 0. So I'll have pi over 2 minus 0, which is just pi over 2. Okay, so sorry about that before. So now that I have these two different values, these two different integrals, I'm going to add them because that's what I originally had going up top. So I have pi over 2 plus pi over 2, which is pi. Okay, let's look at a quick little theorem, and then I think we're going to have to switch to a new recording. Okay, so real quick, just this theorem. I have the integral from 1 to infinity of 1 over x to the p dx is going to be convergent if p is greater than 1 and divergent otherwise. The only thing that this is good for is that if I give you the integral, if you look at number 1, we had the integral from 1 to infinity of 1 over x squared dx, and it was convergent. And then if we did the integral from 1 to infinity of 1 over x dx, it was divergent. If I give you the integral from 1 to infinity of 1 over x to the 1/2 dx, or 1 over square root x dx, it will diverge. Okay, if I give you the integral from 1 to infinity of 1 over x cubed dx, it will converge. Okay, and not only will it converge, but it will converge to 1 over p minus 1. Okay, so this will converge to 1 over 3 minus 1, because our p is 3 here, or a half. Okay, so if I were to evaluate this integral, I would get a value of a half here. If you're an awesome memorizer, then you can memorize this. If you're not, then you can just evaluate your integrals. If you have a homework problem that utilizes this theorem, you can use it. Just make sure that your bounds are actually from 1 to infinity. Also, when we come to series, I'm going to recall this, so you better remember it then. Okay, we are done. I'm out of time, so I'm going to do a second video for dealing with infinite discontinuities in our functions.